All right, so today's notes in section 2.4 are about solving multi-step inequalities. And that's our goal for today. So I have like a list of steps that help us think about it, which you're welcome to pause the video and copy down. But it's just like solving equations. What we want to do is try to simplify each side. If there are variables on both sides, we want to collect them, and then our overall goal is just to get the variable all alone. So we're going to use this list of steps to go through a few examples today. And the big thing here, when you're doing solving inequalities, the only thing that's really different than solving equations is just remembering to watch out for when you multiply or divide by a negative. Because if you multiply or divide by a negative number, you just have to flip the inequality symbol. So as we're doing these examples, we're just going to watch out and ask ourselves, are we ever multiplying or dividing by a negative? Other than that, everything is very, very similar in regards to solving. So on this one, just as a quick little point of view, when we have multiple operations, like right now x is being divided by 2, and then when it's adding 4, remember when you're undoing or when you're solving, it's best to go backwards through the order of operations. So I'd want to undo addition and subtraction first. So I'd subtract 4 from both sides. And now here I do not want x to be divided by -2, so I'm going to multiply both sides by -2. Now in your head, when you multiply by a negative, I want that little bell to go off in your head and say, I just multiplied by a negative. So when I multiply by a negative, that inequality symbol needs to change its direction. So these are all the x's that are less than 10. So open circle at 10, and we'll shade less than that. Right away with this one, I want to look at one other common way to do it. It's very common for people to want to undo division using multiplication and do that as your first step, which is totally fine. But if you're going to do that, you just have to remember to multiply all terms. I like to think of it as like a little balance. If I have 10 plus 5 on the left side, that's clearly equal to 15. If I'm going to multiply these things by numbers, if I only multiply some of them, like maybe I multiply the 10 and the 15 by 2, but not the other one, it's no longer true. I would need to multiply everything on that scale to make sure that it stays true. So the same thing happens here. When I'm going to multiply by a -2, well, first of all, the ding's going off, because I'm multiplying by a negative. So I know that this inequality symbol has to change directions. But everything needs to be multiplied by -2. The x divided by -2 and the 4. And over here we get +2. We'll see that we get the same exact answer no matter what we do, but just a different method. So let's move on to number 2. Again, I see multiplication and subtraction, so I'm going to want to undo subtraction first by adding 2 to both sides. And this is -9. Now here I'm dividing by 3. That's not a negative number. The number that I chose to divide by is positive, so I do not need to do anything with the sign. We'll graph the solution. So a closed circle at -3, and -3 is bigger than all of my c values, so I'll shade left. We don't want this 8, so we're going to subtract 8, so we have nothing on both sides. We don't lose our negative. Now here I'm going to divide both sides by -9. So the ding is going off because I divided by a negative, which means I have to flip the inequality symbol. So I'll graph that as well. We'll put 4 on the number line, a closed circle at 4, and 4 is being eaten by the inequality symbol, so my c's, or the numbers that I'm going to shade in, are less than that. Last one we have here, again, similar problem to number 1. I see a 5 and division. I think it's best to subtract 5 from both sides first. So 1, and we don't lose our negative. And just remember, when it comes to a fraction, put the negative either on the top or the bottom, just not both. So I like to put it on the bottom, so I know that if I'm going to undo dividing by -3, I would multiply both sides by -3. The bell's going off in my head because I just multiplied by a negative number, so I'm making sure to flip the inequality symbol. So we have all the v's that are bigger than or equal to -3, so a closed circle, and we'll shade to the right. So as we move forward to our next example, if there's variables on both sides, as we said right here, we should just get them on the same size by using inverse operations. So on this one, when I see x's on the left here and I see x's on the right there, I want to get them on the same side. So I don't want any x's on the right side, let's say. So if I don't want any x's on the right side, I would need it to be 0, so I'd subtract 3 x's from both sides. And then it looks very similar to the ones we were working on the front page. I want to undo subtraction first. And I don't want x to be multiplied by 2, so I'm going to divide by 2. And I did not divide by a negative, so I am not flipping the sign. And again, we'll just make that graph real quick. The inequality symbol is opening towards the numbers that we are going to shade in other words, the x's, so we shade the numbers that are bigger than 5. Here again, I see that we have variables on the left and the right, so my first step should be getting them on the same side. I don't want any x's on the right side, so if I wanted 0 x's there, I'd have to take away 2 from both sides. And then again, it looks very similar to what we were just working on. I'd want to isolate the x value, undo addition and subtraction first. And here I'm just dividing by regular old 4, so I don't need to do anything special. All my x's are less than 4. So moving on, again, when we working with inequalities, sometimes we have special situations where all the x's cancel out, or all the variables cancel out. We've seen that with equations before, like 3x minus 6 equals 3x plus 6. When I subtract 3 x's from both sides, I got negative 6 was equal to 6. And the idea here is very similar to when we work with equations. If the resulting inequality is true, then it's all real numbers. If the resulting inequality is false, then there's no solutions. So the way that we graph that, we'll see in a moment, but if we're saying that we have all real numbers, what that means is every single number on a number line would work. And you can see that in purple. No matter what I plug into the inequality, it's always going to be true. So we literally shade the entire number line. If there's no solutions, we don't shade anything. We might mark a 0 on our graph just so we know where it is, but if there's no answers, there's nothing to shade in. So let's watch out for those special situations here. Now, on this one, I do see variables on different sides, but I'd want to simplify the right side first by using the distributive property. So as we did before, if there's variables on the same side, I don't want any on one side. So like for me, I don't want any t's on the right side. So if I had 6, I'd need to take 6 away. If I had 6 t's and I took away, there's nothing left. So just the 10. Over here I had 6, but I took 6 away, so there's nothing left. And I asked myself, is this true? Is negative 4 bigger than 10? And that's false. So that means there's no solutions, which I'm just abbreviating. And again, what that means is no matter what I plug in into that inequality, it's always going to simplify to something that's not true. So let's try t equals 1. So 6 times 1 is just 6. 6 minus 4 is 2. Now on the other side, 3 times 1 is just 3. And twice of 8 is 16. And 2 is not bigger than 16. So we're saying no matter what I plug in, it's not going to work. So on my graph, maybe I'll just label 0, but there's nothing to shade in because nothing works. Looking at number 6, I see I can simplify the left side of the inequality first by using the distributive property. So to get all the x's on the same side, I don't want any on the right side, so I'd have to take all 4 away. What I do to one side, I have to do to the other. So they just go away. 4x take away 4x is nothing. If I had 4 x's and I took away 4 x's, I have nothing. Now this one, 9 is bigger than negative 3. This is true. So here, this means all real numbers work. No matter what number I choose to plug in, it's going to work. So let's just try an easy one like x equals 1. 2 times 1 is 2. On the other side, 4 times 1 is just 4. So twice of negative 1 is negative 2. And 9 plus 4 is 13. Is negative 2 less than 13? Yeah, that's true. So just a quick example showing one value, but what all real numbers means is no matter what number I choose, it will always be a solution. So we're shading in the entire number line. I'm putting the arrows at the end to indicate that my shading would go on forever and ever and ever. I just can't shade every single number possible. So a quick application to do for today. So your grade on 4 math tests were 79, 85, 86, and 88. And we want our mean grade to be at least 85. So we need to write and solve an inequality to determine what grade we get on our 5th test to get our goal. So as we've always been working with applications or word problems, the question or the command can help us identify our variable. So if I need to write an inequality to determine what grade I got, that should be my variable. I need to find that. So if I don't know it, it must be an unknown value. So that's a variable. So X can be the grade on the 5th test. Notice how I'm just taking that language directly from the problem. The second thing when working with inequalities, it's really nice to know that inequalities compare two things at once. So we have a goal score, and then we have, well, maybe I should call it a goal grade, be a little more appropriate. And then we have our average grade. And what we want our grade to be at least 85. So my grade could be 85 or it could be bigger than 85. So we just start to supplement, or maybe substitute, values that we know. Our goal grade is 85. Now our grade needs to be bigger than or equal to that in order for us to achieve our goal. And just remember that the mean, that's another word for average. So we add all things up and divide by the total. So I would have to add up all my grades and divide by how many there were. So the first test I got a 79, then I got an 85, then I got an 86, then I got an 88, and I don't know what I got on the 5th test yet, which is why we called it X. So that's 5 scores, so I'm going to divide this by 5. So I'm going to simplify that inequality. I'm just going to add up all those numbers on top. And obviously you'd be able to use a calculator to do that. So I'm just going to add up the scores that I know. So that comes to 338 plus X divided by 5. So now we want to get X alone. I do not want the numerator to be divided by 5, so I'm going to multiply everything by 5. Now 85 times 5, that brings us to 425, so I'm going to have to write up here for a second. We didn't multiply by a negative, so I'm going to keep my inequality symbol. And when I look at this side, the only reason I multiplied by 5 was to undo dividing by 5. So multiplying by 5 and dividing by 5 should simply undo each other. So that 338 plus X is unaffected. And now it's fairly easy to get X alone. We're just going to subtract 338 from both sides. This brings us back to 2.2. We know that adding and subtracting is really easy to do. When we are working with inequalities, there's nothing special to look out for. So we get this. We see that our score on the 5th test is being eaten when it's compared to 87. So that means we need to get at least an 87 on the 5th test. And that's our notes for today.